Figure 5 represents the plan view of part of a smooth horizontal floor where RS and ST are smooth fixed vertical walls. The vector RS is in the direction of I, so we can think of that as just being horizontal there. And the vector ST is in the direction 2I plus j. We'll come to that a bit later. So what do we want to know here? A small ball B is projected across the floor towards RS. We can see that in the diagram. Immediately before the impact with RS, the velocity of B is 6I minus 8j. So I think I might just add to the diagram here that this is 6 and it's 8 in this direction. And the ball bounces off RS and then it hits ST. The ball is modeled as a particle. Given that the coefficient of restitution between B and RS is E, find the full range of possible values of E. Well, that's where we're going to come to this one, where we know that this is 2 and 1, 2i plus j, and that means that the gradient here is a half. So in order for this to have an impact, we must have a situation where the gradient is less than a half. If it was equal to a half or greater, it would go up here and never impact again. So if we know that the coefficient of restitution is E, when it reflects back up, because it hit this horizontal surface, the horizontal component's not changed, but the reflection up here will be 8 times E. So the gradient of this line is going to be 8E over 6, and that needs to be less than the gradient of ST, which we know is a half in order for the impact. So that's E is less than, so it will be 6 over 16. So E is less than 3/8, and of course E is always a positive constant, so E must be greater than 0. Now for the second part of the question. It's given that E is a quarter and that the coefficient of restitution between B and ST is a half. Find in terms of I and j the velocity of B immediately after its impact with ST. So that's along this bit here. Now the reason this bit is tricky is because of the angle of ST. There are various different ways of coping with this, but I'm going to use one where I'm actually going to rotate ST and make it horizontal. And that's why the first part of the question was relatively straightforward, because this was horizontal. If I can make this one horizontal, then that's going to really help. And of course, I have to rotate the other vectors as well. Let's call the angle here theta. Now, if we do that, let's deal with that angle to start with. So we know that this was 1 and 2. We dealt with that in the first part of the question. And that makes this one root 5. And that means that sine theta is 1 over root 5. And cos theta is 2 over root 5. Now, if we know that the E was a quarter, we also can figure out this vector just here, because we now know that that component is 6. Let's just draw it here. So we know that that is 6, and that's going to be a quarter of 8, which is 2. So that's our velocity vector going inwards. So how are we going to rotate? Well, we know from other work that we've done, this rotation vector for an anti-clockwise rotation. So anti-clockwise. But if we want a clockwise rotation, it's just going to become cos theta, sine theta, negative sine theta, cos theta. And the reason it's going to do that is that we know that cosine is an even function. So cos of negative theta is equal to cos of theta, but sine of negative theta is equal to the negative of sine theta. And so that's how we get to this clockwise rotation, because if we're going to rotate this so that it's flat, we're rotating in a clockwise direction. And the angle we're rotating by is theta, and we've already looked at theta up here. So our rotation vector would be 2 over root 5, 1 over root 5, negative 1 on root 5, and 2 on root 5, which is 1 on root 5, 2, 1, negative 1, 2. Now this is just a scale factor, so what we're going to use is just the 2, 1, negative 1, 2. And as long as we use that throughout, it's not going to make any difference to our answers. So if we do that, 2, 1, negative 1, 2, 2, 2, 1, which is the vector st, what do we get? We get 5, 0. And now that's nice and horizontal, exactly as we would like it. We have to rotate the other vectors as well, and we'll do that now. So we discussed the incoming velocity, which in this picture is going to be 6, 2. What's it going to be when we rotate? So we are going to rotate it. So 2, 1, negative 1, 2, and rotate 6, 2, and that will be 14, negative 2. So what we have is a vector coming in like this, such that this is 2 and this is 14. And then we want to think about the vector coming out. We were told in the question that for this one, E is a half. So now that we have it nice and horizontal, which is why we did all this rotation, this is still going to be 14. That's just going to be a half of 2, which is 1. And we are after this velocity vector. This is the one we're after. But of course, we can't just give it as 14, 1, because we need to rotate back so that it's this vector here and not our rotated vector. So let's just call the vector we want uv. 2, 1, negative 1, 2 times the vector we want is 14, 1, which is our rotated version of that vector. And therefore uv is going to be 2, 1, negative 1, 2 inverse times 14, 1. So inverse the matrix, so we can see the determinant is 5, so we're going to have 1/5. If we swap the 2's, that doesn't make any difference. Take negatives on the other, and so we get that. And so that is going to be 1/5 of 28 take away 1, 27, 14 add 2 is 16, and that gives us the vector 5.4, 3.2 meters per second.